identity. That was all Bezout's identity, right? So we have Bezout's identity for polynomials, right? That was one of the homework problem we did then. So we have Bezout's identity. It all works, right? Monic into monic irreducibles. Yeah, yeah, right. Yeah, this is true. It's true. All right. Yes. Yeah. There's no money tied to that, but it is correct. All right. Going a little bit further. It's a fundamental theorem of arithmetic for polynomials. Every non-zero monic polynomial is a unique factorization, right? So we have that. Here's a fundamental theorem also. What happens here? Fundamental theorem of arithmetic of polynomial. I just changed rational number to real numbers, right? Still true. Still true. But what's down there? More interesting statement. Actually, all the monic irreducible polynomials are either linear or quadratic. There's no other. If you enter real coefficients. Yeah, that's strange, isn't it? For irreducible, you have every order. If you degree 5, there will be infinitely many degree 5 irreducible polynomial with a rational coefficient, but real numbers, no. Gauss even gave you a wrong proof. It was proved after 1900. Did you believe that? This fundamental theorem of algebra was correctly proved after 1908 or something. There was a little gap in their argument for all those grades. We tried this one. Okay, that was a strange statement. Here's so I'm going to skip that one. So that turns out to be reducible if you use quadratic formula. And here's the case. I looked at this x to the third minus x plus 3, real coefficients, right? And it should factor into linear or quadratic, correct? According to the fundamental theorem of algebra. So I actually try to factor it using Mathematica. Mathematica doesn't do it automatically. You have to play with it a little bit. Here's a linear factor, the 0 of that polynomial. And the other quadratic using synthetic division, you get this one. And it's really irreducible. You can't reduce it any further. And that is the factorization of that polynomial. So I entered one higher degree. The theory says it should factor into linear or quadratic, right? It does not have linear factor. If you sketch it, it never touches the real axis. It's hovering over. So here's a quadratic and here's a quadratic. And the coefficients is approximate values like this. I actually multiply them out. You can see there's almost 3. You can see that's almost 1, right? It's a 0. You can see it's almost 3. Almost -1 is almost 0, right? Presenting this factorization like this, you're more suspicious that I'm not sure if it's unique. It seems that by looking at this number, it's not easy to understand why there's a unique factorization. If you look at like degree 40, and if I claim that this is a unique factorization with this ugly coefficient, it's a lot harder to believe. I'm not sure that's actually unique. Maybe there's a different way of factoring it. But the fact is that it's unique. And that's the polynomial side. And even though it's considered as a deep result, factoring polynomial over the real numbers is not so interesting arithmetically. And this is a more interesting area, and that's what we've been doing so far. Okay, well, that's enough.